Lecture 36, Continuity and Change in Cognitive Development. In closing this series of lectures, I want to talk about some overarching themes in our study of psychological development. The earliest theories of development focused on problems of maturation and learning. In general, these theories offered a view of the child as what you might call a short, stupid adult who grows smarter as he or she grows bigger. Viewed in this way, there is a continuum of childhood and adulthood, only quantitative differences with no abrupt qualitative changes. We can see this view in a classic study of development by Arnold Giselle, one of the founders of developmental psychology, who trained some children, these were actually twins, in walking and climbing stairs. Twin T received training early on in life, while twin C, the control twin, did not. In fact, the trained twin did show walking and climbing earlier than the untrained child, but the untrained child quickly caught up and further progress wasn't accelerated by training. Both children advanced beyond walking at the same rate. The conclusion is that walking and climbing are behaviors that just emerge at the appropriate time as the child grows older. Another study involved traditional Hopi children who are swaddled and bound to a cradle board for the first year of life. Except for a relatively short period of time each day, they're held pretty much immobile, severely restricting motor behavior. But it turns out that once released from the cradle board, there is no retardation in the emergence of walking. So, in the Giselle case, the training didn't affect the development of walking. And in the Hopi case, the cradle board didn't affect walking either. It just happened when it was time for it to happen. In fact, Giselle and his colleagues introduced a set of developmental schedules which indicated various milestones in development, the point at which the average child would be expected to show certain kinds of motor or adaptive behaviors, use language in a particular way, or show certain personal or social characteristics. Normal children achieve these milestones just by the process of maturing as a function of growing older. Turning to cognitive development, perhaps the clearest example of the view of development as quantitative change is the measurement of intelligence by Binet and Simon in France and by Terman in the United States. We all remember that Binet measured intelligence in terms of the child's mental age, which he assumed was correlated with chronological age. Lewis Terman adopted the idea of mental age when he introduced the formula for calculating the intelligence quotient, or the IQ, as the ratio of mental age to chronological age times 100. And, for that matter, David Wexler did much the same thing when he came up with the idea of deviation IQ, so that an individual with an IQ of 100 has the same IQ test score as the average person in his or her age group. In each case, the underlying assumption appears to be that normal children will simply grow more intelligent as they grow up. Despite debates over the heritability of IQ, the classical continuity view is that the child gradually acquires knowledge through learning, where learning was construed as tantamount to the sorts of things we studied in the lectures on classical and instrumental conditioning. John Locke, an English philosopher of the 18th century, famously argued that the infant is a tabula rasa, or blank slate, who is written on by experience. In the Lockean view, development is a matter of learning more than you already know. This contrasted with the earlier view of Descartes, who assumed that some knowledge was innate as a gift from God. Whether the theoretical focus is on biological maturation or on learning, in either case the process of development is viewed as a matter of continuous quantitative change. The infant starts out small, physically and mentally, and gets bigger, physically and mentally, as he or she grows up. Later theories of development, especially theories of cognitive development, began to focus on qualitative changes. In this view, the child is not just a short, stupid adult. Rather, the young child thinks differently than older children and adults do. Thus, the developmental differences between younger and older children are qualitative in nature, differences in kind, not just differences in amount. Children are not stupid compared to adults, but their intelligence needs to be appreciated on its own terms. This was the view of development propounded by Jean Piaget, a Swiss psychologist who actually worked with Alfred Binet at an early stage of his career, but who argued that the development of intelligence proceeds through a sequence of stages, each defined by certain cognitive landmarks. An important concept in Piaget's theory is the schema, a term familiar from the lectures on the perceptual cycle and also Sir Frederick Bartlett's work on memory. For Piaget, a schema is an organized mental structure that produces a particular coordinated response to a certain class or category of stimuli. Thus, a schema is a kind of concept that renders diverse objects functionally equivalent. That is, you respond the same way to them because they all belong to the same class. In a very real sense, for Piaget, cognitive development is the development of schemata, their elaboration and differentiation as a result of experience. The interaction of schemata and the objects with which they come into contact is characterized by the twin processes of assimilation and accommodation. By virtue of assimilation, the mental representation of the stimulus is altered so that it will fit into the schema employed to process it. By virtue of accommodation, the schema itself is modified so that it can process the stimulus. Thus, the final representation of the stimulus is a sort of a compromise between what was expected, the initial schema, and the actual stimulus itself. Piaget believed that the neonate confronts the world with a primitive set of innate schemata. Through assimilation and accommodation, the nature of these schemata gradually changes. At certain points, however, the changes in mental schemata are so dramatic that they appear qualitative in nature rather than merely quantitative. And these shifts mark the child's move from one stage of cognitive development to another. Each of these shifts, in turn, is marked by the child achieving some landmark behavior. The first of Piaget's stages is sensory-motor intelligence, also known as the sensory-motor period, which encompasses about the first 2 years of life. In this stage, the world of the child is one of unrelated sensory experiences and reflex-like motor reactions to them, sensory and motor activity. To take a phrase from William James, the world of the sensory-motor infant is a blooming, buzzing confusion. But not quite, because according to Piaget, the child has these innate sensory-motor schemata that it uses to deal with the world. One of these schemata might be described as, if you touch an object, put it in your mouth. That works pretty well if you're an infant nursing, but infants put all sorts of other things in their mouths. The object is assimilated to this sensory-motor schema. One of the major accomplishments of the sensory-motor period is the development of object permanence. For Piaget, the newborn's behavior is tied to what comes through its senses. Out of sight is out of mind. A child will look at a toy that's placed in front of him and probably try to put it in his mouth. Once the toy is blocked from view, the child just loses interest. It's as if it's not there anymore. This is because, during the sensory-motor period, the child doesn't have the ability to form mental representations of stimuli. The child can only react to the physical presence of the stimulus. Eventually, however, the child comes to behave as if it has internal mental representations of objects that are not actually present in its sensory environment. So at this point, if a toy is hidden from view, they'll look for it. This searching behavior shows that the child has an idea of the object that persists despite its physical disappearance. During the sensory-motor period, then, the child shows a failure of object permanence. The first landmark of cognitive development, achieved about 24 months of age, is object permanence, the child shows that he or she has acquired the capacity for forming internal mental representations, memories, if you will, of the outside stimulus world. At this point, about 24 months after birth, the infant moves fully into the next stage of cognitive development, the pre-operational period. The child is able to form and retain internal mental representations of objects and events, but these representations exist as individual mental units, unrelated to each other. The major achievement of the pre-operational period is the ability to relate one representation to another through higher-order schemata called operations, and this takes about the next 5 years. The development of operational modes of thought is marked by the emergence of conservation, which occurs by the time the child is about 7 years of age. In the earliest portion of the pre-operational period, the child just does not conserve at all. He shows conservation failure. If a short, wide cup of liquid is poured into a tall, thin glass, the child may well say that there is more liquid in the former than the latter. This is because the child can track changes in either height or diameter, but not both simultaneously. Thus, the child cannot understand that volume, which is a product of height and diameter, remains constant when the liquid is poured from one container into the other. The same thing goes for conservation of mass. If you take a thick lump of clay and stretch it out into a thin straw, the child may well say that there is less clay than there was before. And if a child is shown a set of objects lined up over a short distance, and later the same objects rearranged over a longer line, he or she is likely to say that there are more objects in the latter case than the former. At some point, however, the child no longer makes these mistakes. He's acquired the ability to consider height and diameter, number and distance, length and width simultaneously, and to compensate for one with the other. At that point, the child has acquired the ability to conserve. An analog of conservation failure in the interpersonal domain is egocentrism, which is not to be confused with selfishness. For Piaget, egocentrism reflects the child's inability to take another person's point of view, or to appreciate the viewpoints of other people. In a sense, egocentrism reflects the child's inability to conserve viewpoint across changes from one person's viewpoint to another. Egocentrism is often assessed with the so-called Three Mountains task, introduced by Piaget and his collaborator Bärbel Inhelder. A child is situated at one end of a display with 3 mountains, and a doll is put at the opposite end. The child is asked if the doll can see the cross, and the child says yes, and that's true. The cross is in both their fields of view. But when the child is asked whether the doll can see the church, she also says yes. She fails to appreciate that the mountain with the cross on top would block the doll's view of the chapel. The egocentric child does not appreciate that other people may have a view of the world that's different from his or her own. Here is some data from a study of age differences in performance on the 3 Mountains task. 4-year-olds tend to give egocentric answers on the Mountains task. They say the doll can see the church when it can't. Egocentrism starts to disappear when the child is 6 on average. By the time the kids are 8 or 10 years old, they're giving the correct answer. They appreciate that the doll can't see something that they can. Like conservation failure, egocentrism is a characteristic of pre-operational thought. And the loss of egocentrism, like the acquisition of the ability to conserve, marks the child's movement from the pre-operational stage to the next stage, the stage of concrete operations. At about age 7, the child enters the stage of concrete operations, in which children are capable of thinking and reasoning about objects and events which they've actually experienced. Concrete operational children are actually pretty powerful thinkers. They can conserve, of course, and they don't show egocentrism anymore. They can pay attention to objects other than the most salient ones in their environment. They can take another person's point of view. They can take account of transformations in state and they can classify objects into groups based on shared properties. They can also generate and use hierarchical classification schemes, schemes involving subsets and supersets and all of that. You can get along pretty well in life with nothing more than concrete operations, as long as you're reasoning about familiar problems involving familiar objects and events, which, after all, is what most of us do most of the time. Unfortunately, concrete operations aren't always enough, especially if you're living in a so-called advanced society. It is often useful to go beyond our own past experiences and to reason about things that we haven't seen or touched, or, for that matter, to be able to reason about things that aren't visible or touchable. Concrete operations just don't suffice for this purpose. So it's a good thing that around age 12, the child enters the last of Piaget's stages, which he called formal operations. In formal operations, thinking can be purely symbolic, without referring to anything at all by way of concrete objects and events. The hallmark of formal operations is scientific thinking, which is what lies behind Piaget's notion of the child as a naive scientist. Scientific thinking is marked by 4 different qualities. First, hypothetico-deductive reasoning, in which we can hypothesize about a certain state of affairs and then reason deductively from that hypothesis. That is, we can assume something is true without actually requiring it to be true. Second, inductive reasoning, in which the person generalizes from specific observations to general principles. Third, reflective abstraction, in which the child is able to reflect on his or her own thoughts in order to arrive at novel ideas. And fourth, propositional logic, in which the child can reason about 2 or more abstract entities that are represented by statements such as, if there is a P, then there is a Q, without knowing what P and Q refer to. Children who have developed the capacity for formal operations are able to deal with several abstract variables at the same time. Of course, Piaget was not the only theorist to offer a conception of development in terms of stages. Long before Piaget, Sigmund Freud had offered a stage theory of psychosexual development running essentially from birth to adolescence. And in the 1960s, Erik Erikson, a follower of Freud's, offered a stage theory of psychosocial development that encompassed the entire life cycle from birth to death. Piaget, Freud before him, and Erikson afterward had an enormous influence on thinking in developmental psychology. Their idea of development as a progression through a succession of qualitatively different stages was received quite enthusiastically. You can see the legacy of these theorists in the proliferation of stage theories of everything in developmental psychology. For example, Lawrence Kohlberg, heavily influenced by Piaget and also a colleague of Erikson's at Harvard, introduced a stage theory of moral development, basically taking Piaget's idea and applying it to moral reasoning, not just cognitive development in general. For Kohlberg, moral reasoning is the basis for ethical behavior, and the individual moves through a set of 6 or maybe 7 identifiable stages throughout development. At early stages, moral reasoning is focused on self-interest. How can I avoid punishment? What kind of reward am I going to get? At later stages, moral reasoning is focused on concrete rules. What am I supposed to do? What do other people want me to do? What are the rules? And in the final stages, moral reasoning is based on abstract principles like justice and equality. You can see how this fits in with Piaget's ideas. Moral reasoning is very egocentric in the pre-conventional stages. The child is concerned about what's going to happen to him or her. It's very concrete in the conventional stages, where the child follows the rules because they're the rules. And it involves abstract reasoning in the post-conventional stages. Stage theories of development of the sort introduced by Piaget became very popular in developmental psychology in the 1960s and 1970s. But just as they came to dominate the field, a number of experimental psychologists found cracks in the edifice, empirical problems that suggested that Piaget's theory, at least, wasn't quite right. One of these problems is known as décalage. For example, the development of operational modes of thought is marked by the emergence of conservation, which occurs by the time the child is about 7 years of age. But if there's really a fundamental shift in thought, a qualitative change, you'd expect this shift to occur relatively rapidly and to be widely generalizable. But that turns out not to be the case. A child who successfully conserves quantity may not conserve mass, and may not conserve number. A child who conserves mass may not conserve quantity, but may conserve number as well, and so on. There just doesn't seem to be this wholesale shift in mode of thought that's implied by Piaget's theory. Moreover, researchers discovered that the lower boundaries of Piaget's stages are not nearly as rigid as he suggested that they were. Is it really true, for example, that children younger than the age of 7 are just incapable of abstract thought? Or that pre-operational children do not have a concept of number? A very large research tradition has developed out of questions like these, and the general conclusion is that cognitive development is probably more continuous than Piaget thought it was, and that even very young children can show amazing powers of thought, at least in limited domains. Such findings undermine the general thrust of the Piagetian stage approach to cognitive development. Let's consider, for example, Piaget's claim that pre-operational children aged 2 to about 7, don't have a concept of number. They're just not capable of it. In one of the earliest critiques of Piagetian theory, Rochelle Gelman and Randy Gallistel analyzed just what's entailed in having a concept of number. Their analysis yielded a set of 3 principles that define correct counting. Counting requires the person to use a set of labels, like the words 1, 2, 3, and 4, and to assign these to objects depending on how many of those objects there are. So the first principle you need is one-to-one correspondence. The items to be counted have to be put into one-to-one correspondence with a set of number tags that are used to count. Second, the stable order principle says that the number tags themselves have to be used in a consistent fixed order. And third is the cardinality principle, which says that the last number word that's used in a count has to represent the number of items that have been counted. So if you and I were counting dogs, we'd say 1, 2, 3, 4, 4 dogs. That count shows one-to-one correspondence. And then if I do it again, 1, 2, 3, 4, 4 dogs. That shows stable order. I've used the same order twice, and the last number I use represents the number of dogs there are. But suppose I'm a little kid, and I don't know my number words all that well yet. You ask me to count the dogs, and I say, 1, 5, 3, 8. 8 dogs. I'm still showing one-to-one correspondence. And I do it again. 1, 5, 3, 8. 8 dogs. I'm showing stable order, and I'm showing cardinality. There are 8 dogs. Now, what I mean by 8 isn't what you mean by 8, but that doesn't matter. I'm still applying the counting principles, and that's the same as if I used no number words at all. Suppose you asked me to count, and I said, Blitz, Blatz, Bluck, Blit, Blit dogs. And you said, do that again. And I said, Blitz, Blatz, Blut, Blit, Blit dogs. I'm still showing one-to-one correspondence. I'm still using my number terms in a stable order, and I'm still showing cardinality from my point of view as a child. I've got a sense of number. It's just not expressed exactly the way you'd like me to express it. Later on, I'll learn the number words, and I'll learn to use them correctly, and I'll count 1, 2, 3, 4, 4 dogs, just like you do. But before then, I've still got a sense of number. Gelman and Gallistel, among others, showed that even pre-operational children, 3 and 4 years old, apply these counting principles in their own way. They've got a sense of number. they know how to count, at a time when Piaget said they don't and they shouldn't know how. So Gelman and Gallistel pushed the concept of number back into the pre-operational stage, which raises the inevitable question, how low can you go? How far back can you push the beginnings of a concept like number? It turns out that, if you're a clever enough experimentalist, you can push it back pretty far. Here's an experiment by Karen Wynn using 4- and 5-month-old infants. They're not fresh out of the womb, but they're pretty young. They're firmly in what Piaget would have called the sensory-motor stage, far away from the boundary that divides sensory-motor intelligence from pre-operational thought. Wynn employed looking time as a measure of attention in these very young infants. The idea behind this measure is that a child who is surprised by something will look at it longer. There are actually 2 groups of infants in this experiment. Let's look at them one at a time. In what Wynn called the 1+1 condition, the infants were shown a single item, like a small mouse puppet, in a display area. Then a screen came up to obscure the mouse. The experimenter then introduced a second mouse, pretty much identical to the first, and then put that behind the screen as well. Then the screen dropped and revealed one of 2 possible outcomes. Either the screen dropped to reveal 2 objects, or the screen dropped to reveal just 1 object. The idea is that if the child is counting, doing anything like adding, he will expect to see 2 puppets when the screen drops. But he'll be surprised to see 1 puppet, and he'll look longer. Similarly, in the 2-1 condition, the infants were first shown 2 mouse puppets. Then the screen came up, the experimenter took one of those objects away, and finally the screen dropped to reveal either 1 mouse puppet or 2 mouse puppets. If the child is doing anything like counting, anything like subtraction, it'll expect to see 1 puppet when the screen comes down, but will be surprised to see 2. And that's just what happened. In the 1+1 condition, the infants looked longer when the screen came down to reveal just 1 item. It's as if they added 1+1, expected to see 2 puppets, and were surprised when they saw only 1. Similarly, in the 2-1 condition, the infants looked longer when the screen came down to reveal 2 items. It's as if the infants subtracted 1 from 2 and expected to see only 1 item, and were surprised to see 2. So the fact that the children in the 1+1 condition are surprised when they see only 1 object, and the children in the 2-1 condition are surprised when they see that there are still 2 objects, suggests that even at this very, very early age, the children are engaged in something like rudimentary addition and subtraction. So this experiment offers what you might think of as a kind of double whammy to Piagetian theory. Remember that these infants are supposed to be in the Piagetian stage of sensory motor intelligence. They respond only to what they can see and hear, and they haven't formed any internal mental representations of the things that they've encountered with their senses. Out of sight, out of mind. But if that were the case, there would be nothing to add to in the 1+1 condition, and there would be nothing to subtract from in the 2-1 condition. After all, there's a screen up there, hiding the objects from view. So it's very clear that even these infants, just 4 or 5 months old, have some sense of object permanence. They know that the object is behind the screen, even though they can't see it, and they can add to and subtract from what they know is behind the screen. If 4 and 5-month-old infants have object permanence, and they already have a rudimentary ability to count and add and subtract, there is really no point in postulating qualitatively different stages in cognitive development. Okay, now let's take a breath and review the bidding. Piaget's theory is a stage theory of development, and like all stage theorists, Piaget argues that the stages of cognitive development are universal, obligatory, stereotyped, and irreversible. All normal individuals must pass through them in the course of development. The stages are passed through in the same sequence for all individuals. Once a stage has been negotiated, there is no going back. And the achievement of one stage is a necessary condition for advancement to the others. These are essentially hypotheses about the nature of development, and it turns out that when they have been seriously tested, research has usually failed to confirm them. In particular, research testing Piaget's theory has revealed a number of anomalies which led investigators to refocus their theories on continuities in mental development, not qualitative changes. One post-Piagetian approach construes development as the development of cognitive skills. According to this view, the infant starts out as a novice in all domains of problem solving and gradually acquires expertise through learning, through experience and practice. However, in this view, expertise is not just a quantitative difference, where experts just know more than novices do. Rather, the argument is that experts represent problems in a qualitatively different manner than novices do. For example, it's been argued that expert knowledge is cross-referenced, so as to enable the problem solver to get easy access to it in a variety of situations. Moreover, expert knowledge focuses on higher-order patterns, so that experts think in bigger chunks and take larger steps in problem solving than novices do. One model for the development of expertise is the difference between novice and expert chess players. Both kinds of players know the rules, but experts represent the game differently and play the game differently than novices do. Now, this may seem like it's just a variant on our old theory of development as learning. Remember our definition of learning as a relatively permanent change in knowledge that results from experience. In the same way, expertise develops with experience and practice. However, there are at least two important differences between the theory of expertise and a mere theory of learning. The first of these is that the acquisition of expertise involves qualitative leaps in skill that represent the individual's successive reorganizations of task performance. These qualitative leaps are, in some sense, analogous to Piaget's stages. But they're not the same as Piaget's stages, because even young children can obtain more expertise than adults. If you don't believe me, ask any 8-year-old boy about dinosaurs. The theory of expertise also doesn't consider the infant as a blank slate to be written on by experience the way the traditional learning theory would. Instead, the child is viewed as bringing a rudimentary cognitive apparatus into the world, such that learning experiences modify his or her innate cognitive propensities. These differences between the modern theory of expertise and the traditional theory of learning reflect, I think, the lasting contribution of Jean Piaget to developmental theory, despite the fact that his theory appears to be wrong in many salient details. Still, theories of expertise seem to imply some degree of continuity over the course of development. But studies of expertise reveal one big difference between younger and older children. Put bluntly, older children typically know what they're doing, while younger ones often don't. Older children are not simply more expert than younger ones at various tasks. They're also more reflective, more deliberate, more strategic in their thought and action. In other words, what older children possess and younger children lack is metacognition, a term first introduced by Lila Gleitman and subsequently popularized by John Flavel. Metacognition is, literally, cognition about cognition, or, put another way, our ability to monitor and control our own cognitive processes. Metacognition is one's knowledge about cognition and cognitive phenomena. Gleitman and her colleagues pointed out that the developing child doesn't just acquire a language. He or she also acquires a meta-language. The child becomes a more competent grammarian and is better able to distinguish between grammatical sentences and non-grammatical sentences. Similarly, Flavel and others pointed out that we develop meta-memory knowledge about the principles that govern how memory works, principles like elaboration, organization, and encoding specificity. So there appear to be at least two different components to metacognition. First, knowledge of what's in your mind, knowing what you know, knowing whether you're perceiving something or just imagining it, knowing what knowledge you have stored in your memory, and whether you actually understand something you've learned when it's been explained to you. The second component is the person's appreciation of the rules that govern various mental processes. How we can deploy attention effectively, how we can use strategies for effectively encoding and retrieving memories, and how we can break down large problems into sub-problems. This kind of knowledge is the hallmark of expertise. It's not just knowing something, but more important, knowing that you know something and knowing how you know something. In fact, Flavel has argued that there are several different aspects of cognitive monitoring, or metacognition, including goals or tasks, knowing the objectives of some cognitive enterprise, actions or strategies, knowing what cognitions or actions you can employ to obtain your goals and complete some task. Metacognitive knowledge, or knowledge about factors that influence your own and others' cognition. And metacognitive experiences, conscious thoughts and feelings that pertain to cognition. When you work on a problem for a while or someone explains it to you, and then you have that aha experience, I've got it, I understand it now. That's metacognition. The general idea is that with development, children become more expert at cognition, but they also develop metacognitive knowledge. They make more conscious, deliberate use of their cognitive faculties. More broadly, we might say that, as they develop, children come into possession of a theory of mind, a term coined by David Premack and Guy Woodruff, imported into developmental psychology by Henry Wellman, and then popularized by Simon Baron-Cohen. He's the cousin of the comedian Sacha Baron Cohen. Put briefly, the theory of mind entails the ability to impute mental states to ourselves and to others. It includes knowledge of our own minds and knowledge of other minds. With respect to knowledge of our own minds, we mean understanding that we have mental states, that we perceive things and feel things. The realization that our experiences are our own, that somehow our experiences are separate from the world outside the mind, and that we can control our own beliefs, feelings, and desires. Knowledge of our own minds also entails phenomenal awareness, introspection, consciousness of what we think, feel, and want. Knowledge of other minds, by contrast, entails the understanding that our mental states may differ from those of other people, that other people have minds of their own, and thus different experiences. And our knowledge of other minds entails an ability to make inferences about what other people think and feel and want, based on what they say and other aspects of their behavior. In some ways, the idea of the theory of mind revives Piaget's notion of egocentrism. For Piaget, the pre-operational child thinks that his experience is universal. But the older child, having entered concrete or formal operations, understands that others may not have the same experiences, may not perceive the world the same way he or she does. In fact, the theory of mind usually emerges between 5 and 7 years of age, exactly the same point as, in Piaget's theory, there occurs a shift from pre-operational thought to concrete operations. The young child's acquisition of a theory of mind is often assessed with what's known as the false belief task. This task involves an experimenter, a child, and a puppet. The puppet hides an object, like a ball, in a container, like an oatmeal container. Then the puppet is put away in a cabinet, and the experimenter and the child switch the ball from the oatmeal container to a box. The puppet is brought back to look for the ball, and the child is asked where the puppet will look. 3- and 4-year-old children who have just put the ball in the box will say the puppet will look in the box. And when asked why, they'll say something like, because that's where it is. By contrast, 4- and 5-year-old children will say that the puppet will look in the oatmeal container. And when asked why, they'll say, because that's where he thinks it is. The 3-year-old apparently doesn't have the ability to appreciate that the puppet's mental state, the puppet's knowledge, is different from hers. But the 5-year-old does have this ability. Here is some data on typical performance in the false belief task. Children who are about 3 to 4 years old, 30 to 50 months, tend not to pass the false belief task. But children who are aged 50 months or older, after they get to be about 4 years old, tend to pass the task. And by the time the children are 6 years old, certainly 7 years old, almost all of them are passing the false belief task. They know what they know, and they have the sense that other people may not know the same things they know. They have a theory of mind in that sense. Now, of course, whenever you set up an age boundary like this, some developmental psychologist is going to come along and say, I wonder if you can get that in younger kids if you ask the question the right way. And the answer is yes. Experimenters have devised very clever nonverbal versions of the false belief task, usually employing a variant of the looking paradigm that I described earlier. And with these kinds of experiments, they've been able to show that infants as young as 15 months, even younger, have some appreciation of the theory of mind, that they may know things that other people don't know. And they may also have some ability to discern the cognitive, emotional, and motivational states of other people. So on this evidence, then, even very young children, still in infancy, have some rudimentary theory of mind. But it turns out that the child isn't just developing a theory of mind. The child is, at the same time, developing a theory of the whole world, of physics and biology and sociology, as well as psychology. The same child who's trying to figure out how other people think is also trying to figure out how the physical world works, and how the biological world works, and how society is organized, how society works, all of it. This is the essential proposition of what has come to be known as the theory of cognitive development. The idea that the developing child is engaged in a continuous process of proposing, testing, revising, rejecting, and elaborating theories of how the world works, including theories of how minds work as part of the world. The theory is the latest stage, if you will, in the evolution of theories of cognitive development, and it's been promoted by Alison Gopnik with her colleagues Henry Wellman and Andrew Meltzoff, among others. These theorists begin, in a sense, with Piaget's metaphor of the child as a naive scientist, actively exploring the world, actively experimenting in the world, formulating hypotheses about how various aspects of the world work, gathering evidence that bears on these hypotheses, and revising these hypotheses in accordance with the evidence. But whereas Piaget argued that the child as a naive scientist was really a characteristic more of formal operations, Gopnik and her colleagues propose that the child is behaving as a naive scientist right from the beginning. The child is engaged in a process of developing theories about the world, abstract, coherent knowledge systems just like scientific theories, except certainly less formal, that the child uses to interpret and explain events and to predict and control what happens in his or her world. How does a child do this? Well, the short answer is through learning. Gopnik and her colleagues proposed that by observing events in the world, children learn about the world from conditional probabilities, the conditional probabilities that link one event to another, and by behaving in the world, by engaging in some activity and seeing what the consequences are, what they call learning from interventions. If you think that learning from conditional probabilities looks like classical conditioning, and learning from interventions looks like instrumental conditioning, you wouldn't be far off. The child is actively engaged in the process of acquiring knowledge about how his or her world operates. And, as I noted in earlier lectures, something like classical conditioning and something like instrumental conditioning, these are very powerful vehicles for acquiring this kind of knowledge. And just as powerful, if not more so, is observational learning, including social learning from others by both precept and example. But wait a minute, it looks like we've come full circle. After all that discussion of Piaget and expertise and metacognition and theory of mind, it looks like we're back to Locke's conception of the child as a tabula rasa, a blank slate that's written on by experience. But that is not the intention of Gopnik and her colleagues. In the first place, they argue that the child brings into the world an innate theoretical capacity, an innate cognitive apparatus that permits the child to form and test and revise his or her developing theoretical understanding of the world. In fact, they go so far as to argue for what they call starting state nativism. This is the idea that the child is actually born with what they call substantive, innate theories of various domains like physics and biology, and, for that matter, mind and society. They are not completely clear on what these innate primitive theories might look like, and maybe they're wrong about that, but still the child is not a tabula rasa. The child comes into the world with an innate capacity for theory, an innate ability to form theories and test theories and revise theories that he or she deploys almost from the beginning of life. This is the sort of innate cognitive capacity that Immanuel Kant was talking about. So it's not the case that the child's mind is written on by environmental events, as John Locke would have had it. Rather, the child is actively engaged in theory testing. In the same way that we describe classical and instrumental conditioning in terms of an organism actively trying to predict and control its world, right from the start, even as an infant, the child is actively engaged in theory testing, trying to understand surprising events as well as he or she can, and to test and revise his or her understanding by conducting experiments, by trying to figure out if this understanding that he or she has actually allows him or her to predict or control events. The child is a scientist, trying to figure things out, and the world, the physical world, the biological world, the world of the mind, and the world of other people, that's the laboratory.